Okay, I'm going to talk about Taylor's theorem. You should have seen Taylor's theorem in calculus. There are some very important ideas in Taylor's theorem. You can see some examples of series that express more complicated functions. These functions, cosine, sine, exponential, are called transcendental functions. They cannot be expressed as a polynomial. However, the Taylor series gives us an infinite polynomial, you could say, that gives us the value of these transcendental functions. This is extremely important in numerical analysis because computers can't compute these directly. Computers can only add and multiply and divide and subtract. So computers can compute these polynomials, but they cannot compute these functions directly. This is one way of computing these transcendental functions. It turns out not to be the best way or the most practical way, but not only is Taylor series useful for computation, it's also useful as a theoretical idea. Think about this. If I have sine, for instance, if I want to approximate sine up to a certain level, then I'll only take a few terms of this series. If x is very small, it may be enough simply to take the first term. And we will many times in numerical analysis want to approximate values of a function very close to a particular value. So for instance, if I want to find sine of x for values of x very close to 0, it may be enough for me simply to take x. All right, so let me go down and talk about a little more ideas. So this is the general expression for Taylor series, this formula here. And you notice that it depends on the derivatives of a function at a particular point. And here's some examples. Here we derive the Taylor series for cosine. The Maclaurin series is simply the Taylor series when you expand about the point x equals 0. This general Taylor series expression means that I'm expanding about the point x, and h is the difference between my evaluation point and my expansion point. Quite often this x is taken equal to 0, and as said above, that's the same thing as Maclaurin series. Now this section is very important because whenever you do an approximation, you really need to know how accurate your approximation is. When I do Taylor series, and here's my Taylor series formula, this gives me the value of the function at x plus h. X is my expansion point. H is the difference between my evaluation point and my expansion point. So if I take n terms of this series, which means I would take up to the nth derivative of f at the expansion point, I'm not going to get an exact value. There's going to be an error. And here's an expression for the error. It depends on h, which is the difference between evaluation point and expansion point. Also depends on the n plus first derivative of my function, evaluated at some point in this interval. Now, you may wonder, if you don't know which point this is, why is this useful? Well, if I know the derivative on the entire interval is less than a certain value, then that means I can give a bound on this error. I can say the error is less than something. Now, you can read this example here, how he bounds the error. In this case, he's using the function e to the x. And if you know, all derivatives of e to the x is e to the x. So he computes this error here. It's going to be e to the c over 24. I know that c lies in a certain interval. So this term e to the c will lie in a certain interval, and I can tell that my error will be between two values. He does more examples of finding remainder terms. Okay, so what I'm going to do is do an Excel spreadsheet that computes Taylor series and shows the error of the approximation.